Welcome, welcome students. Welcome to the gas turbine lecture 4. In the previous lecture, we have learned about the ideal gas turbine cycles. Okay, but in practice, uh, it is difficult to achieve those ideal conditions. Okay, so therefore, now we are going to discuss about the performance of the practical gas turbine cycles by taking into account the different losses in different components. Okay, so before going into the details, and let's see the various assumptions. And another thing, in this lecture we will see the various assumptions, or first of all we will see the various assumptions, and we will derive the efficiency for gas turbine and for compressor, and we will also derive the relation of the work ratio. Okay, so let's start. First of all, let's see the assumptions, okay, for of these practical or actual gas turbine cycles. So as the fluid velocities are high in turbo machinery, the change in kinetic energy between inlet and outlet of each component will be taken into account. Okay, number two is the compression and expansion process are irreversible adiabatic, involving increasing in entropy. Okay, the compression and expansion, that means the compressor work and the turbine work are the irreversible adiabatic, but in case of ideal process, that was reversible adiabatic or isentropic process. But here this expansion and compression work are the irreversible adiabatic. Number three is fluid friction results in pressure losses in combustion chamber and heat exchangers, and also the inlet and exhaust ducts. Number four, the complete heat exchange is not possible in heat exchanger. The mass flow is assumed to be same in spite of the addition of fuel. This is justified because the bleeding of air from the compressor, which is around 1 to 2% for cooling the turbine disc and blades root, is compensated by the addition of fuel. Then the values of Cp and gamma of the working fluid vary throughout the cycle due to the change of temperature and due to the change in chemical composition of the working medium. Okay, and last one is slightly more work than the required for compression process will be necessary to overcome the bearing and windage friction in the transmission and to drive auxiliary components. Okay, so these are the assumptions. So the compressor and turbine efficiency. Uh, the actual simple gas turbine cycle is shown in this figure. Okay, the TS diagram. During the compression process, the considerable amount of energy is supplied to the compressor is wasted in cheering up the working fluid, and this energy does not contribute the pressure rise, but it's converted into the heat by friction. So the outcome is that the temperature of the working fluid is higher at the end of compression, and it would have been had the process been fully and truly isentropic. The compression process on the TS diagram will therefore be represented by the line that is a 1 2. As you can see, this is 1 2, this is a curved line 1 2. Okay, the temperature at 2 is, that means the temperature at here at point 2 is higher than the at point 2 dash. Okay, that 1 to 2 dash is the isentropic process, that is a reversible adiabatic process, and 1 to 2 is irreversible adiabatic process. Again, 1 to 2 dash, that means the straight line process. Okay, the constant entropy, the straight line process is the straight line process. Okay, it's 1 to 2. The straight line process is the straight line 1 to 2 dash. The straight line 1 to 2 dash is a constant entropy and reversible adiabatic process. 1 to 2 dash, this straight line, and 1 to 2 is the irreversible adiabatic process. This 1 to 2, okay, is the irreversible adiabatic process. So from this diagram we can see that the temperature at 2 being higher than at 2 dash. Okay, so which is the temperature that would have been reached by isentropic compression over the same pressure ratio. Because of this, the more work input to the compressor is required, and thereby the efficiency of the compressor comes into picture. Okay, so the efficiency of the compressor is given by, or is we can define as the isentropic compression work by the actual compression work. Isentropic compression work, this is the isentropic compression work, that is 1 to 2 dash by the adiabatic or actual compression work. Okay, that is the reversible adiabatic compression work by the irreversible adiabatic compression work, that is the isentropic compression work, the numerator, and in denominator is the actual compression work. Okay, so this is the enthalpy. Okay, this h2 dash h1 to 1. Okay, so now we are converting this enthalpy into the temperature, that is the T1. This point temperature is T1. The temperature at this point is T2 dash, and this point temperature is T2. Okay, T2, T2 dash, and T1. Okay, so the compressor efficiency becomes T2 dash minus T1 by T2 minus T1. Okay, so because of the total pressure ratio or stagnation pressure ratio of the compressor, we are assuming at RC. Okay, so that is the T2 dash by T1 dash is equals to RC to the power gamma minus 1 by gamma. Okay, because 1 to 2 dash, this is the 1 to 2 dash line, this is the straight line, this straight line is a isentropic work done. So we are calculating this the pressure ratio for this work. Okay, so now from this equation we can write, so T2 minus T1 is equals to T1 by eta C. Eta C is the compressor efficiency into RC to the power gamma minus 1 by gamma minus 1. This relation is comes from here, the compressor efficiency equation. Okay, so now the compressor work, the compressor actual work is defined as WC act. Okay, so that is nothing but that is equals to the Cp into T1 by eta C, Cp into T1 by eta C into Rc to the power gamma minus 1 by gamma minus 1, because this work done is T2, this temperature difference is T2 minus T1. Okay, so we know the work done formula is mcpdt. Okay, so for unit mass flow rate, or for unit mass of fuel, m is 1, and by multiplying cp with this temperature difference, by multiplying this cp, okay, with this temperature difference, this T2 and T1, we get the actual work done, the actual compressor work done. Okay. Now in case of turbine efficiency, that is eta t, eta suffix t. In case of turbine efficiency, we can write the actual turbine work output by the isentropic turbine work output. Okay. The actual turbine work output, is defined by this 3 to 4 is the actual turbine work output by the isentropic turbine work output. Isentropic turbine work output is defined by this red line. Okay, the red straight line with the constant entropy line. Okay. So in this case, this isentropic work output is higher than the actual cycle work output. So the actual cycle work output, the actual turbine work output by the isentropic turbine work output in denominator. Okay. So that becomes T3 minus T4 by T3 minus T4 dash. Okay. So we are again the assuming R suffix T is the total pressure ratio of for in case of turbine expansion process. Okay. So in case of isentropic process, T3 by T4 dash, T3 by T4 dash equals to RT to the power gamma minus 1 by gamma. T3 by T4 dash equals to RT to the power gamma minus 1 by gamma. So the R3 minus R4, that means the temperature difference for actual turbine process, the actual turbine working process, the temperature difference T3 minus T4 is becomes eta suffix T. Eta T is the turbine efficiency into T3 into 1 minus 1 by RT to the power gamma minus 1 by gamma. So again, the turbine WT turbine work output, actual turbine work output, that is WT actual ACT act, WT actual, that is CP into this temperature difference, the CP into this temperature difference. So we get the actual turbine work output. Okay. So that is CP into eta T into T3 into 1 minus 1 by RT to the power gamma minus 1 by gamma. Now the net work done. Okay. The net work done. Net work done is nothing but same as previous. The turbine work, actual turbine work minus actual compressor work. This is the turbine work that we have already derived minus the compressor work. Okay. And this is the expression for net work done. Now the work ratio is nothing but the net work done by the actual turbine work. So that becomes 1 minus actual compressor work by the actual turbine work. Again 1 minus actual compressor work by the actual turbine work. That means net work done by the turbine work. Okay. This is the work ratio. This is the work ratio. Net work done by turbine work. So if we assume that is the pressure ratio in case of compressor, in case of turbine, and is equal, and that is equals to R, and substituting this RC RT and equals to R, this value into this work ratio equation, this equation. So let's see what we get. So that is 1 minus T1 into R to the power gamma minus 1 by gamma minus 1 by eta C eta T into T3. Okay. So 1 minus C by small t into 1 by eta C eta T. This is the ideal expression for work ratio. Here small c is the R to the power gamma minus 1 by gamma, and T small t is the ratio of the temperature difference, that is the maximum temperature by the minimum temperature. The maximum and minimum temperature difference ratio, the maximum and minimum temperature, that is T3 and T1. The maximum temperature and minimum temperature ratio is small t. Okay, so this is the expression for work ratio. So we can see the work ratio increased by high temperature ratio and low pressure ratio. The work ratio is increased by high temperature ratio small t and low pressure ratio. Okay, so let's solve a numerical. Says that an oil gas turbine installation consists of a compressor, a combustion chamber, and a turbine. The air taking in at a pressure of 1 bar and the temperature of 30 degrees Celsius, the compressed to 6 bar with a isentropic efficiency of 87%. The heat is added by the combustion of fuel in the combustion chamber, rises the temperature to 700 degrees Celsius. The efficiency of turbine is 85%. The calorific value of oil is 43.1 megajoule per kg. Calculate for airflow of 80 kg per minute. Neglect the effect of fuel in mass flow rate. Calculate number 1, the air fuel ratio of the turbine gases, the final temperature of exhaust gases, the net power installation, and number 4, the overall thermal efficiency of the installation. Assume Cp of air is 1.005 kilojoule per kg Kelvin and gamma for air, that is 1.4, and Cp for gas is 1.147 kilojoule per kg Kelvin and gamma for gas, that is 1.33. Okay. So as it says that the pressure is compressed from 1 bar to 6 bar, that means at point 1 the pressure is 1 bar and at point 2 dash is 6 bar. So let's first find out the temperature of T2 dash. T2 dash is equals to T1 into P2 by P1 to the power gamma minus 1 by gamma. So T1 temperature is 30 degrees Celsius, that is 303 into 6 to the power gamma minus 1 by gamma. Gamma value for air is 1.4, so that becomes 0.02857. So the T2 dash value is 505.5 505.5 Kelvin. Okay, now find the T2 value, the temperature at this point after compressed, uh, the actual in actual process, the temperature of T2 is T1 plus T2 dash minus T1 by eta C, the compressor efficiency. So by substituting all these values, we get the T1 value is 303, T2 dash value is this 505.5, this is T1, and eta C is 87%, so that becomes 0.87. So the value of T2 becomes 535.8 Kelvin. Okay, 535.8 Kelvin. Now, as in the question, it says that neglect the effect of fuel in the mass flow rate. Okay, so we are going to neglect the mass flow rate uh, effect. So the m dot f plus m dot a is nearly equals to m dot a, the mass flow rate of air. So we have to find out, first we have to find out the mass flow rate of fuel, m dot f. So that is equals to m dot a into cpg, the cp of gas, into the temperature difference, the combustion temperature difference, that is T3 minus T2. T3 is the end of combustion, okay, temperature, and minus T2. T3 is the end temperature, end combustion temperature, and minus T2 is the initial combustion temperature, the temperature at the starting of the beginning of combustion, by the CV. So and the m dot a value is given, that is 80 kg per minute, so that is 80 by 60 kg per second. CP value is given, CP of gas is given 1.147, and T3 is 973 minus T2 that we have already calculated by the CV, that is the CV value is 43.1 megajoule per kg. So the value of a mass flow rate becomes 0.0155 kg per second. So the mass flow rate of air by the mass flow rate of fuel becomes 80 by 60 into 1 by 0.0155, so that becomes 86. Okay, so the air fuel ratio becomes 86 is to 1, or simply 86. Okay, so now let's find out the temperature of T4 dash. Okay, temperature of T4 dash. T4 dash is the temperature if the turbine follows the reversible adiabatic process or the isentropic process, and T4 is the outlet temperature of the T4 dash. T4 dash is the outlet temperature of the turbine in ideal case. So that is equals to T3 into P4 by P3 to the power gamma minus 1 by gamma, and T3 value is 973 into P4 by P3 is nothing but 1 by 6 to the power gamma of air is 1.4, so that is 0.2481. So the T4 dash becomes 623.8 Kelvin. Okay, now the value of T4, okay, the actual temperature, actual turbine exhaust temperature, the actual turbine outlet temperature, that is T4, that is equals to T3 minus turbine efficiency eta T into T3 minus T4 dash. So the value of the T4 becomes 672 676.2 Kelvin. Now the net power, that is W suffix n, the net power by neglecting the fuel, we get the by neglecting the fuel flow rate, we get the turbine work, the actual turbine work minus the actual compressor work. Actual turbine work is the actual turbine work again minus the actual compressor work. Okay, and here for in case of turbine work we are substituting m dot a, that is the mass flow rate of air instead of mass flow rate of fuel, because in the question it's given that it says that neglect the fuel effect, so we are just neglecting the mass flow rate of fuel effect. Okay, so instead of mass flow rate of fuel we are substituting here the mass flow rate of air. So mass flow rate of air into Cpg, that is the gas, Cp of gas, into T3 minus T4, the actual temperature difference, the actual expansion work temperature difference, minus m dot a, mass flow rate of air, into Cpa, Cp of air, into T2 minus T1, that is the actual temperature difference in case of compression. So by substituting all these values, okay, we get the actual work done, that is 142 kilowatt. The actual work done as 142 kilowatt. Now the overall thermal efficiency, that is net power by heat input. The net power by heat input. So the net power that we have already calculated now, that is 142 kilowatt by this 0.0155, that is the mass flow rate of fuel that we have already calculated, into the CV, the calorific value of fuel. Okay, 43.1 megajoule per kg into 100. Again, 142 is the net work. 142 is the net work. This network, okay, this value, and 0.0155 is the mass flow rate of fuel that we have already calculated, into 43.1 or 43100 joule per kg or 43.1 megajoule per kg. This value is the calorific value of fuel into 100. So the overall thermal efficiency of this plant is 21.25%. 21.25%. So in this lecture we have derived or the efficiency, the actual efficiency in case of turbine or in case of compressor, and we also derived the work ratio, and we have done a small numerical here. So in the next lecture we will do some other types of numerical on this actual cycle turbine. Okay, thank you.